All right, day 23, we're back for part 2. We've got an example here. A boat's located exactly west of boat A rather, is located exactly west of boat B. Boat A has a velocity of 51 kilometers straight south, and boat B has a velocity of 80 kilometers on a bearing of 230 degrees. Will the boats collide? And this is kind of a strange question, but this is a relative velocity question. So the idea is, um, this boat's going this way, this boat's going this way. It looks like they're going to collide, but how do we handle this? Well, we're going to use relative velocity. So we're going to put ourselves on this boat, boat A, and we're going south at 51 kilometers, and this one is 80 kilometers on a bearing. And notice I've drawn a scale diagram. You don't have to. You could pause it and draw a decent job. One thing that's strange about this, we don't know the distance between them. We just know that one is west of the other. But if we're on this boat and the two boats are going to smash together, what should it look like? Well, it would look like this boat is coming straight towards it, right? So the question is this happening? Is this going to happen? And we saw the relative velocity of them, boat B, to us, who's on boat A. And we could have done it the other way, but this is, I think, just simpler, is B minus A. Now, we need to actually construct this diagram, right? Now, I've done a scale shot of this, and I'm going to use some smartboard magic and copy these vectors and draw the result. Okay, so see if I can do this. Copy. I'm going to paste that vector. There she is. So this is B. B. And then minus A. So I'm going to make a copy of A. And of course, you could just draw it too, right? But there's A. And now, where's minus A? I'm going to flip her up the other way. And if I draw them tail to tail, I'm kind of going off. But let's draw them tip to tail. So this is B and minus A. This is 51 and this is 80. And it looks like the resultant, R, is this vector right here. And it certainly looks like boat B is going to smash right into boat A according to our diagram. But let's be exact. We're going to actually calculate some values here. So the idea, I think, is if this angle here, if it's 40 degrees, we're smashing. Smashy smash. If we find theta and it ends up to be 40 degrees, then it's a collision. Now notice, I can't say this looks like a right angle triangle, but I can't assume that, right? Because that would, if this is 90, I know this is 50 because look at the Z pattern here. If we had put our direction crosshairs here, we know this is 50. We can't say that that's 90 because then this would be 40 and we'd be answering our question with an assumption, which is no good. But I know that that's 50, so this is 50. If I want to find this angle, I need an angle side pair to use the sine law, or I need all three sides to use the cosine law. I'm going to have to find the magnitude of the result anyway. The magnitude of the result is 51 squared plus 80 squared. Cosine law, we've got 1,000 of these already this year. No big surprise here. And hopefully you see how that's 50, right? Because that's 50, and then this would be straight south, north, and the vectors are parallel, so that's 50. And then bada boom, bada bing. pound it into a calculator, make sure you take the square root at the end. I've got it to be 61.3 kilometers per hour. And so the boat, if you're on boat A, it'll appear like boat B is traveling somewhat toward you. We don't know exactly toward you, but it'll be at 61 kilometers per hour. Now, what's the direction? This is the fun part. This is whether we determine it's a smashy smash or not. Sine theta over 51 is our angle side pair that we have now. Sine 50 over 61.3. And bing, 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 calculator, calculator, it's just about 40 degrees. So if that's 40 degrees, and again, the idea is, why does that tell us? That means the relative velocity of B compared to A is straight west, right? This is 40 degrees. This is straight west, and that's how they started. And the velocity is moving straight west. They will collide. Fun. Okay. From home, Ferd walked 2 kilometers at a certain bearing for 3 hours, then jogged 5 kilometers for 1 hour. What is his displacement from home? So let's draw a diagram. I'm not going to do it to scale. Don't care about scale here. I'm going to sort of draw my little direction crosshairs here. See if I can get them both on one time, make them small. That, and the original north, 50 degrees east. North, 50 degrees east is off this way somewhere. I'm going to put an arrow on the end of it. Label that maybe. That's 50. Now, the thing is we want displacement, which is not velocity, right? So we're going to have to figure out actually how long this vector is. Well, if he's 2 kilometers per hour for 3 hours, that's 6 kilometers he's moved, right? So this is 6 kilometers long. And then he's moved 5 kilometers per hour straight south for 1 hour. So how much has he moved? He's moved 5 kilometers south. And again, I'm going to, can I copy this one? Sure I can. Why not? Because now he's moved straight south from there. 5 might be around there somewhere, something like that. Oopsie. There. That's 5. And then his displacement from home is, overall, this is the direction he's moved in. So I'm going to put that in there. Oops. I got little tiny arrows all over the place. Let me get rid of them. And I'm going to make this a different color just so it stands out for me. And that is the displacement vector. Let's call it D. Again, the hardest part in these questions is finding the angle, because I know I want to find the magnitude of this and the direction, which will be this angle in here, but I need an angle in my triangle, right? And I get it from the direction. It's nice when one of them is straight south or north or west or east, because then it's pretty easy to see that this is 50 here, isn't it? And then now I'm off to the races again. Cosine law. Good thing we did all that trig practice in September. Or I guess well, early in the semester. And around 4.7. Check that on your calculator. Thank you very much. 4.7 kilometers is this distance. And so notice, this isn't his distance traveled. His distance traveled would have been 11 kilometers. His displacement is 4.7. This is 4.7 kilometers right here. Now what direction? Well, I call that theta, then I can sort of use that angle and figure out which bearing that I'd like to write it as. Sine theta over 5 is equal to sine 50 over 4.7, and that's all this is approximate because we rounded our last answer. And then cross multiply inverse sine, and I get the angle is about 55 degrees-ish. So if this is 55, then I could see the displacement then is 4.7 kilometers on a bearing of 50. This is 50, and then another 55, 105 degrees. That's the bearing. What's the average velocity for the trip? Well, the average velocity is just sort of the total velocity over the time, right? Well, the total velocity is this display. Or sorry, the average velocity is the total distance over the time. Excuse me. Let's tidy that up. Is the total displacement over the time, and that displacement was 4.7 kilometers on that bearing. But how long did he move for? 3 hours plus 1 hour, 4 hours, right? So on average, 1.2 kilometers per hour on a bearing of 105. So he could have got there, instead of walking this way and jogging this way, he could have got there if he just moved at 1.2 kilometers per hour on that red bearing. That's his average velocity. Notice his average speed would be somewhere between these two, because he moved 11 kilometers in 4 hours. Right? So his average speed would be that, where this is the distance. It's different, isn't it? Average velocity and average speed. What do we got? One more? One more, eh? Two cars, one traveling south and one traveling east, collide at an intersection. The resulting momentum of the two cars together after the collision is big number at that bearing. Okay, find the momentum of each car. So one's traveling, and this is just a rough sketch here. Black maybe. So one's moving, one's traveling east, and one's traveling south. And another smashy smash right there. And they end up, and this isn't to scale again, they end up, and this is maybe where I want to do a decent job of diagram so I get an angle right. The resultant vector is south this way and 30 degrees east. Okay? Where if I put my direction crosshairs there, try and make those small again for you. South 30 degrees, this here is 30 degrees, right? And then even though these vectors don't make sense really, but this one's momentum is this component, right? And this one, if I fix it up, is the east component, south component of the collision vector, and the east component of the collision vector, where this one here is the resultant, right? This is the resultant momentum vector. Put R on there, and I can see that this one was, don't know, This is the southern component. This is the eastern component. And then the resultant, I know, is 3,800. This component business from earlier in the chapter. This is rectangular components. And was somewhat more simple because it was in a right angle triangle. So this one should be fairly straightforward. If I wanted to find S, that's the adjacent side. So I'm going to use the cosine of 30 degrees is the adjacent side over the hypotenuse. And I can see that the southerly component is a little bit higher, right? So cross multiply and you get about 32,000, almost 33,000 kilo. I guess that's the units for momentum. It's kind of like a physics thing, I guess. And then the sine is the easterly component. And again, these are special angles, but we're just firing it into a calculator at this point. And so the two components are of the momentum vector are this kilogram meters per second south, and this kilogram meters per second east, right? So those are the two components. Perhaps I should have a sentence, but just let's keep going. How could you determine the speed of each car before the collision? Well, the little momentum is the mass times the velocity. Now you wouldn't know that unless you took physics, but I'm here to tell you. And that kind of makes sense because if you look at the momentum units, there's mass, there's velocity. It's all good. So here's the momentum. If I wanted to find the velocity, well, all I would have to do is divide by the mass. Right? This is the divide by the mass of each car. Then you could find the velocity, and then of course the speed is just that velocity south or that velocity east. Good. Done. Good luck on your homework and then your review, right?